All right, so the next topic, it's not really a test for convergence, but they are going to ask you on your AP exam. They're going to give you a series and they're going to say, does it converge absolutely or conditionally? So I'm just going to start with this example. And we have this alternating series, right? -1 to the power of n makes your series alternating. So let's just first, let's do it the regular way, use the alternating test and see what happens to this series. And we are going to consider the two separate conditions and see if both work. So as n approaches infinity, 1 over square root of n is the same as 1 over n to the power of 1/2. Now, the exponent is 1/2 less than 1, so that means this series diverges because, I'm sorry, one second, I'm not doing that right now. I'm doing the nth term, sorry, I apologize. As n approaches infinity, n gets, well, you do the square root of n, and gets bigger and bigger and bigger, the whole limit approaches 0. So the first condition works. Second condition, you need to make sure this inequality takes place. And yes, it also works. So that means this alternating series converges by the alternating the series test. Now imagine we have an absolute value sign around. So what happens to this expression? Does it affect your -1 to the power of n? Of course, because if we didn't have absolute value sign, that would be -1, 1, -1, 1. But with the absolute value sign, no matter what your n is, you take the absolute value and the expression is going to be positive. So this is going to be equivalent to 1 over the square root of n. Now, how about this series? Is this convergent also? No, because you get a 1 over n to the power of 1/2, and that's a p-series, and your exponent is less than 1, so we know that this series diverges. So here's my conclusion. It is convergent, and we just proved it up here, but it's conditionally convergent because when I took the absolute value of this expression and tried to figure out, then I got the divergent series. So, but I'm going to show you the next example. But sometimes what happens, you do it the regular way, you test and your series is convergent, but then you take the absolute value and you again analyze and you determine that it's also convergent. So if it's convergent in both cases, then you say this series is absolutely convergent. So that means when you consider the absolute value, your series was still convergent. So in this case, it's convergent but conditionally convergent. So I hope that makes sense. So let's try B. And it's -1 to the power of n plus 1 over 3 to the power of n. So let's use alternating series test and see what happens to this series. So we take the limit, we're doing the nth term test, n approaches infinity, so we ignore this part right here first, and we're doing 1 over 3 to the power of n, which gives us a 0 because as n gets bigger, the whole denominator becomes bigger, and then the fraction becomes smaller. So that works. And then the second condition, 1 over 3 to the power of n plus 1 should be less than, so less than 3 to the power of n, I'm sorry. So, and that also works. So that means so far our series is convergent. Okay, now let's take the absolute value of this whole thing and see what happens in that case. Okay, so when you do -1 to the power of n plus 1, but its absolute value, you simply get a 1 over 3 to the power of n. And no matter what your n is on the bottom, well, it's greater, you start with 1 and then 2, 3, and so on. So the denominator is positive anyways. So this is what you get. Now, let's check this series. Is this convergent or divergent? Well, this is a geometric series, and since your ratio is 1/3 less than 1, so that means this series is also convergent. So it's convergent here. We use the alternating series test, and it's still convergent after we inserted the absolute value sign. So you say that this series is absolutely convergent. Absolutely convergent. Okay, now in this video I want to talk about the ratio test, and that's a very, very important test because that is going to appear on your free response as well. So let's say you have this series start at 1, a sub n, so here. Now we have three conditions, three statements to make. So the first one, your series converges if you take the absolute value, by the way, limit as n approaches infinity, you take the absolute value, and all you do a n plus 1, you just add 1 to n, but then divide it by the expression, the original expression with n in it, and if it's less than 1, the whole result, then you say it's convergent. The second statement, it diverges if the limit of this same ratio is greater than 1. Now, the third statement, the ratio test, you say, is inconclusive. And that's the word you use if the limit as n approaches infinity of that same ratio all of a sudden equals to 1. So if you want your series to be convergent, then make sure the ratio test, when you apply the ratio test, the limit as n approaches infinity with the absolute value of a sub n plus 1 over a sub n less than 1. And if it's less than 1, then it's perfect. Your series is convergent. So let me show you a couple of examples. So example A. We start at 1, so 2 to the power of n over n factorial. The ratio test usually is helpful when you deal with n factorial, when you have a number to the power of n. So the first thing comes to my mind, the ratio test. And it's pretty simple. So this is what we're going to do. We're going to take the limit as n approaches infinity, the absolute value, and we're just going to add 1 to n. But then we're going to divide it by the actual original sequence, whatever they give us, 2 to the n over n factorial. Now, let's try to simplify. So it's 2 to the n times 2 to the first times, flip the second fraction, so n factorial is on the top now. You have n plus 1 factorial on the bottom, and 2 to the n moves down. Now you notice that you can get rid of these guys here. So let's see what we have left. We have 2, we have n factorial. On the bottom we have n plus 1, which is equivalent to n plus 1 times, we talked about it in class, n factorial. Now again, we can simplify even more, and we end up with 2 over n plus 1. Now, as n approaches infinity, your result equals to 0, right? The denominator gets bigger, the whole fraction becomes smaller. Now let's go back. So when you apply the ratio test and your result is less than 1, then you say that your series is convergent. Next example, B. And again, I noticed I have 2 to the power of n, and whenever I see that, usually, or n factorial, the ratio test comes to my mind, unless it's a simple geometric series. Well, in this case, but you know what, in any case, when they give you a series and they want you to determine if it's convergent or divergent, you always apply the nth term test, no matter what. So you find the limit as n approaches infinity and see if your denominator grows faster than the numerator. And in this case, it's 2 to the power of n. So, well, let's take the limit and see what happens. It's n squared times 3 to the power of n plus 1 over 2 to the power of n approaches infinity. So you can actually play with it. You can plug in 1, 2, 3 and see which one goes faster. I can rewrite it to help you to see which one actually does grow faster. See, you have on the bottom 2 to the n, but on the top you have 3 to the n. Of course 3 to the n grows faster, so the numerator grows faster, and as n approaches infinity, the whole thing approaches infinity. So this is a typical multiple choice kind of question, so you don't want to do anything here because your series is divergent. Okay, so that's very important to apply the nth term test. C. n plus 1 factorial over 3 to the n. The nth term test, let's see which one grows faster. So limit as n approaches infinity, that we can express as n plus 1 times n factorial over 3 to the n. You know what, I guess here you don't even need to do this. You just have to remember that a factorial always grows faster than exponential. That's obvious, and you can play with your calculator just to confirm that. So remember, if you have factorial on the top and exponential on the bottom, the factorial grows much faster. So the whole thing approaches infinity. So this series is also divergent. Okay, and I want to show you, it's not in your packet, but I do want to show you one more example, because the previous two problems, we used the nth term test, and our series, both of them were divergent. So the nth term test here shows us that, let's see, so we have a factorial on the bottom, which always goes faster. Then that means the limit in this case equals to 0. So our series might converge. Now, since we have factorial here, so we want to try the ratio test. So we're going to do the limit as n approaches infinity, add 1 to n, add 1 factorial, and then divided by, because we're talking about the ratio, by the original equation. I'm going to skip this limit for now. I'll add it at the end, by the way, absolute value. Okay, so we get n plus 1 squared times, we're going to flip the second fraction, and it's 2n minus 1 factorial. On the bottom we have 2n plus 2 minus 1 times the nth squared. And then we get, let's see, n plus 1 squared to n minus 1 factorial. On the bottom we get 2n plus 1 and n squared. I just noticed I forgot to include the factorial symbol here. So it's 2n plus 1 factorial. Now we have n plus 1 squared, still 2n minus 1 factorial. On the bottom, what's 2n plus 1 factorial? It's 2n plus 1. Then it goes minus, subtract 1, it's 2n. Then it's going to be 2n minus 1, and so on, right? So I can put 2n minus 1 factorial. So instead of so on, I'm just going to stop there and say, so 2n plus 1 factorial is equivalent to 2n plus 1, then one step down 2n, one step down 2n minus 1, and then it goes 2n minus 2, 2n minus 3, so which is 2n minus 1 factorial. I forgot the n squared because it's sitting right there. Okay, so let's see. We can cross out these guys, and we end up with n plus 1 squared on the top, and on the bottom we have 2n times n squared, which is 2n cubed, and 2n plus 1. So let's see. As n let me just copy it here. So limit as n approaches infinity. So we got n plus 1 squared, I believe. Yes. And then we got 2n cubed, and then 2n plus 1. So we have here, it's n squared. On the bottom here, it's 4n to the 4th. So the result is, since in the numerator exponent is below less than the exponent on the bottom, so your limit equals to 0. So less than 1. So, and that tells you that this series is convergent. And by the way, the ratio test, by the ratio test, you say this series converges absolutely. So it's converges absolutely because we use the absolute value, so absolute value sign.